Right now, while you are lying here, the universe is approximately 93 billion light-years wide. Every second, it grows wider. Every second, galaxies that were once neighbors are now drifting further apart, carried by a fabric of space that is stretching in every direction simultaneously. And at the center of all of this, at the absolute origin point of everything you have ever touched, seen, breathed, or loved, there is a question that science has not yet answered. What was here before any of this existed? Not what came first, not what triggered the explosion, but what was the nature of reality in the moment before reality began? Was there silence? Was there darkness? Or was there something far stranger? Something our minds were not built to comprehend? You are about to find out how deep this question actually goes, how it broke our best models, how it forced the greatest minds of the 20th century to completely rewrite the blueprint of creation, and why the answer, whatever it turns out to be, might be the most terrifying and the most elegant thing the human species has ever uncovered. If this is the kind of content that makes the silence feel a little less empty, subscribe to Sleepy Cosmos. New journeys through the dark every week. We begin now. To understand what came before the Big Bang, we first need to understand what the Big Bang actually was, because almost everything you have been told about it is incomplete. And some of it is wrong. The popular image is simple. There was nothing. Then there was a massive explosion, and from that explosion, the universe was born. That image is almost entirely misleading. The Big Bang was not an explosion in the way we understand explosions. An explosion happens inside space. It expands outward into something. The Big Bang was not an expansion into pre-existing space. It was the expansion of space itself. Space did not exist before it. Time did not exist before it. There was no location where it happened because location requires space, and space was being created in the event itself. When physicists say the universe began 13.8 billion years ago, they do not mean that some cosmic bomb went off in an empty void and sent matter flying outward. They mean that 13.8 billion years ago, space, time, matter, and energy all came into existence together, simultaneously, inseparably, which immediately raises the most profound question a human mind can ask. If time began at the Big Bang, then the question what happened before the Big Bang might be as meaningless as asking what is south of the South Pole. Not hard to answer. Not unanswered, literally meaningless. A question built from broken grammar. But before we accept that comfortable escape hatch, we need to travel back through history. Because the story of how humanity arrived at the Big Bang is not a clean line of progress. It is a sequence of brilliant minds, stubborn assumptions, accidental discoveries, and staggering reversals of everything we thought we knew. And it begins not with a bang, but with a man who believed, with total certainty, that the universe had always existed and always would. The year is 1687. England is cold and grey. A man named Isaac Newton, arguably the most analytically powerful mind ever born, has just published a work that will define scientific thinking for the next 2 centuries. Newton's universe is infinite. It is static. It has no beginning and no end. All the stars hang in perfect, eternal stillness, balanced against one another by the same gravitational forces that pull an apple from a tree. The universe of Newton is elegant in its simplicity, permanent, trustworthy. The kind of universe that does not ask difficult questions about its own origin. There is just one problem. If the universe is infinite and filled with an infinite number of stars, then wherever you look in the night sky, your line of sight must eventually hit a star. Every single point on the celestial sphere should be covered by the surface of some distant sun. The night sky should not be dark. It should be blazing white, brighter than noon on the hottest summer day, burning with the combined light of infinite stars. But you have seen the night sky. It is dark. It is almost entirely black, punctuated by a few thousand points of light. This problem would later be named Olbers' paradox, after the astronomer Heinrich Wilhelm Olbers, who articulated it clearly in 1823. But its implications cut directly to the heart of Newton's eternal, infinite, static universe. The universe is dark at night. Therefore, it cannot be infinite and eternal and filled with stars in every direction. Something is wrong with the model. Newton himself was aware of the gravitational instability problem. In an infinite static universe, gravity should eventually pull everything together into one catastrophic collapse. He resolved this, not with mathematics, but with God. He proposed that the divine hand periodically corrected the cosmos, preventing the collapse. It was not a scientific answer. It was a placeholder. A gap filled with faith where understanding had not yet arrived, and that gap would remain open for more than 200 years. The year is 1915. The place is Berlin, Germany. The continent is at war, and a 36-year-old patent clerk turned professor named Albert Einstein has just completed what many physicists still consider the single greatest intellectual achievement in human history: general relativity. Before Einstein, space was a container, an empty stage on which the drama of the universe played out. Matter moved through space. Forces acted across space. But space itself was passive, inert, just there. Einstein destroyed that picture entirely. What Einstein showed through 10 years of brutal mathematical labor is that space and time are not two separate things. They are one thing: space-time. A four-dimensional fabric woven together. And this fabric is not passive. It responds to mass and energy. It curves, bends, stretches, and warps in the presence of matter. What we experience as gravity, the pull that keeps you anchored to your chair right now, the force that holds the moon in orbit, the invisible hand that keeps the Earth circling the sun, is not a force at all in Einstein's picture. It is the curvature of space-time. Mass tells space-time how to curve. Curved space-time tells matter how to move. The entire gravitational universe is geometry. It was and remains a staggering idea. But when Einstein applied his new equations to the cosmos as a whole, when he tried to describe not just a planet or a star, but the entire universe, his equations did something alarming. They refused to hold still. The mathematics kept insisting that the universe must be either expanding or contracting. It could not be static. It could not just sit there. Space-time, filled with matter and energy, was inherently dynamic, inherently restless. The universe, according to general relativity, was moving. Einstein did not believe this. He was so committed to the idea of a static, eternal universe, the comfortable Newtonian picture, that he did something extraordinary. He added an extra term to his equations, a fudge factor he called the cosmological constant. It represented a kind of cosmic anti-gravity, a force pushing outward against the gravitational pull of matter, allowing the universe to remain in equilibrium. It was, as Einstein would later describe it, the greatest blunder of his life. Because 12 years later, an astronomer in California would point a telescope at the sky and see something that made the static universe impossible to defend. Something that proved Einstein's original, uncorrected equations had been right all along. The universe was not standing still. it was running away. The year is 1929. The place is the Mount Wilson Observatory in the San Gabriel Mountains above Los Angeles. The night air is cold and clear. An astronomer named Edwin Hubble sits at the controls of what is, at that moment, the most powerful telescope on Earth. Hubble has been studying nebulae, fuzzy patches of light scattered across the night sky that earlier astronomers had assumed were gas clouds within our own galaxy. But Hubble has discovered something unsettling. Some of these nebulae are not gas clouds at all. They are entire galaxies, vast spinning systems of hundreds of billions of stars, each one as massive and complex as our own Milky Way. The universe is not just our galaxy. It is a collection of galaxies, billions of them stretching outward into distances so enormous that the numbers lose meaning. But that is not the discovery that changes everything. What changes everything is the color of the light. Hubble notices that the light coming from distant galaxies is shifted, not randomly, but systematically. The light is shifted toward the red end of the spectrum, and the further away a galaxy is, the more its light is red-shifted. This phenomenon, redshift, is the light equivalent of the Doppler effect. When a sound source moves away from you, the sound waves stretch out, lowering the pitch. When a light source moves away from you, the light waves stretch out, shifting toward the red end of the spectrum. The galaxies are not stationary. They are moving, and they are not moving randomly. They are all moving away from us. Every single one. In every direction, and the further away they are, the faster they are receding. The universe is expanding. This was not a metaphor or a theoretical prediction. It was an observational fact written in the light of 10,000 galaxies across the sky. Space itself was growing. The fabric of the cosmos was stretching, carrying galaxies apart from one another, like dots on an inflating balloon. Einstein visited Hubble at the Mount Wilson Observatory in 1931. He looked through the data, he acknowledged the result, and he removed his cosmological constant from the equations, that desperate fudge factor he had inserted to keep the universe still. But the implications of Hubble's discovery went far beyond proving that the universe was expanding. They pointed backward in time. If the universe is expanding now, if everything is moving apart from everything else, then the further back in time you go, the closer together everything must have been. Wind the clock back far enough, and everything converges. Everything was once in the same place. There was a man who understood this before almost anyone else, a man who did not wait for Hubble's data, a man who looked at Einstein's equations and followed the mathematics wherever it led, without flinching. His name was Georges Lemaitre. He was Belgian. He was a Catholic priest. And in 1927, 2 years before Hubble published his observational data, Lemaitre had already predicted that the universe was expanding and drawn the logical conclusion from it. If the universe is expanding now and was smaller in the past, then trace it back far enough, and you reach a beginning. A moment when all the matter and energy of the cosmos was compressed into a single, unimaginably small, unimaginably dense point. Lemaitre called it the primeval atom, the cosmic egg, a seed of infinite density from which all of creation hatched. When Lemaitre presented his idea to Einstein, Einstein reportedly told him, "Your calculations are correct, but your physics is atrocious." Einstein was wrong. What Lemaitre had described, this violent primordial beginning, would eventually be confirmed by evidence so overwhelming, so precise, so convergent from multiple independent directions, that today it is the foundational framework of modern cosmology. It would eventually be given a name by a man who initially meant it as an insult. The astronomer Fred Hoyle, a fierce defender of the alternative steady-state model of the universe, once referred to Lemaitre's theory dismissively on a BBC radio program in 1949 as "this Big Bang idea." The name stuck, but here is where the story becomes genuinely strange. Because the Big Bang theory was confirmed not by seeing backward in time, not by watching galaxies recede, not by calculating their distances. It was confirmed by something far more unexpected: by silence. In 1964, two young radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey. They were not cosmologists. They were not trying to confirm or deny the Big Bang. They were trying to calibrate a large microwave antenna so that Bell Labs could communicate with satellites. They had a problem. No matter what they did, no matter where they pointed the antenna, no matter how carefully they cleaned and recalibrated the equipment, there was always noise. A persistent, faint, uniform hiss coming equally from every direction in the sky. It was there during the day and during the night. It was there in winter and in summer. It did not correspond to any known radio source. Penzias and Wilson even found pigeon droppings in the antenna and cleaned them out, suspecting the birds might be the source of the signal. The noise remained. Frustrated, they reached out to physicists at Princeton University who had been working on a theoretical prediction. In the 1940s, the physicist George Gamow and his colleagues had proposed that if the Big Bang really happened, if the universe really began as a hot, dense inferno of matter and energy, then the heat from that initial fireball should still be present today, not as visible light. The universe had expanded so dramatically in the intervening 13.8 billion years that the wavelengths of that ancient light would have been stretched almost beyond recognition, stretched all the way from the high-energy radiation of the early universe to long, cold microwaves. This ancient light should be everywhere, uniformly distributed, coming equally from all directions. A faint, cold whisper of the universe's violent birth. When the Princeton physicists heard about Penzias and Wilson's mysterious noise, they recognized it immediately. Penzias and Wilson had not found a fault in their antenna. They had not found pigeon droppings causing electrical interference. They had found the echo of creation. The signal they detected, later named the Cosmic Microwave Background Radiation, or CMB, is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, at the moment when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. Before that moment, the universe was an opaque plasma, so hot and dense that light could not travel more than a tiny distance before being absorbed and re-emitted. The universe was like the interior of a star, blazing and impenetrable. At 380,000 years after the Big Bang, the plasma cooled enough to become transparent, and the light that had been trapped in that plasma, the light of the entire blazing early universe, was suddenly free. It flooded outward in every direction. That is the light Penzias and Wilson detected in 1964, 14 billion years later, stretched and cooled by the expansion of the universe to a temperature of just 2.7 degrees above absolute zero. Penzias and Wilson won the Nobel Prize in Physics in 1978. The Big Bang was no longer a theory, it was an observational reality. In 1990, the COBE satellite, the Cosmic Background Explorer, measured the CMB with extraordinary precision. What it found confirmed something that the Big Bang theory had predicted down to the finest detail. The CMB has what physicists call a perfect blackbody spectrum. This means that the distribution of its energy across different wavelengths matches exactly the mathematical shape that you would expect from an object that was once in perfect thermal equilibrium. A hot, dense object that was exactly the same temperature throughout. Not approximately, not roughly, exactly. The probability of obtaining a measurement this perfect from any source other than the actual thermal radiation of the early universe is, for practical purposes, 0. The universe was once a hot, dense, smooth plasma. It cooled, it expanded. The light from that plasma is still here. We have measured it. We have mapped it. It is as real as the ground beneath your feet. And the story was confirmed from yet another independent direction: the proportions of elements in the universe. If the Big Bang really happened, then in the first few minutes, in the first 3 to 20 minutes after the singularity, the universe would have been hot enough for nuclear fusion to occur. Not in stars. In the fabric of space itself, the entire early universe would have functioned as a nuclear reactor. And the physics of nuclear fusion is extraordinarily precise. We know exactly what happens when protons and neutrons collide at specific temperatures and densities. The Big Bang model predicts that this early period of nucleosynthesis would have produced hydrogen and helium in a very specific ratio. Approximately 75% hydrogen, approximately 25% helium, with trace amounts of lithium and a few other light elements. Look at the actual universe. The universe as it exists today, measured across billions of galaxies in the oldest and most pristine regions of space, where no star formation has yet altered the original composition. And you find exactly that. 75% hydrogen, 25% helium. 3 completely independent lines of evidence: the expansion of the universe, the cosmic microwave background, the elemental abundances. All 3 pointing to the same conclusion, with the same precision. The universe had a beginning, approximately 13.8 billion years ago. And from that beginning, everything that exists today emerged. But the classical Big Bang theory, elegant and powerfully confirmed as it was, had problems. Not small problems, not minor discrepancies that could be smoothed over with a more careful calculation. Fundamental, structural problems. Problems that reveal deep cracks in the foundation of the model. 3 of them specifically. 3 anomalies that the standard Big Bang model could not explain. 3 places where the universe refused to cooperate with the textbooks. The first is called the horizon problem. The cosmic microwave background is, as we have established, extraordinarily uniform. The temperature of this ancient light is the same in every direction, 2.7 Kelvin, with variations only in the 100,000ths of a degree. This uniformity, at first glance, seems unremarkable, but consider what it actually implies. The CMB we observe today comes from regions of the early universe that were, at the time the CMB was emitted, so far from not even light traveled between them. They were beyond each other's quantum. No signal, no particle, no energy could move between these regions in the time available. And yet, they are at exactly the same temperature. In physics, 2 regions reach the same temperature through a process called thermal equilibration. They exchange energy until they equalize. But thermal equilibration requires contact. It requires that signals can pass between the regions in question. How can regions of the universe that have never been in contact, regions that are causally disconnected, have reached the exact same temperature? The answer, according to the classical Big Bang model, is they cannot. There is no mechanism. The uniformity of the CMB is, in the classical framework, an extraordinary coincidence. An initial condition of the universe that had to be set, with staggering precision, by some mechanism the model cannot describe. The universe handed physics a mystery, and the standard Big Bang had nothing to say. The second problem is called the flatness problem. General relativity allows for universes of different geometric shapes. The universe can be positively curved, like the surface of a sphere, where parallel lines eventually converge. It can be negatively curved, like a saddle where parallel lines eventually diverge, or it can be flat. Euclidean geometry, where parallel lines stay parallel forever. The curvature of the universe is described by a parameter called omega. If omega equals exactly 1, the universe is perfectly flat. If omega is greater than 1, the universe is positively curved and will eventually stop expanding and collapse. If omega is less than 1, it is negatively curved and will expand forever. Measurements of the actual universe indicate that omega is equal to 1 to extraordinary precision. The universe is flat, or so close to flat that no measurement we have been able to make can detect any deviation from perfect flatness. Here is the problem. In the standard Big Bang model, a flat universe is an unstable equilibrium, like a pencil balanced on its point. Even the tiniest deviation from flatness in the early universe would have been amplified enormously by the expansion of the cosmos. A universe that is even slightly positively curved at the Big Bang will rapidly become far more curved as it expands. A universe that is slightly negatively curved will rapidly become far more negatively curved. For the universe to be as flat as it is today, 13.8 billion years after the Big Bang, the initial conditions at the very beginning must have been set with a precision of roughly 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. In the denominator, the universe's flatness was not the natural, probable outcome of a Big Bang. It was an extraordinarily, almost impossibly fine-tuned initial condition. The classical Big Bang model provided no explanation for why the universe would start in such an improbable state. The third problem is called the monopole problem, and it is perhaps the most technical of the three. In the 1970s, grand unified theories of particle physics, theories attempting to unify the strong, weak, and electromagnetic forces into a single framework, predicted that the hot, dense conditions of the early universe should have produced large numbers of exotic particles called magnetic monopoles. These are hypothetical particles that carry a single magnetic pole, just a north or just a south, rather than the paired north-south poles of every magnet we have ever observed. The grand unified theories were well supported by other evidence. The predicted monopoles should have been created in huge numbers in the early universe. They should be everywhere. We should be detecting them constantly. We have never detected a single magnetic monopole. Not one. 3 fundamental problems. The universe was too uniform. It was too flat. And it contained none of the exotic particles that the physics of the time predicted it should. The Big Bang theory was right about the broad picture, but something was missing. Something happened in the very earliest moments of the universe that the standard model did not account for. Something that stretched, smoothed, and violently reorganized the infant cosmos before a single proton had yet formed. The year is 1979. The place is Stanford Linear Accelerator Center in California. A young theoretical physicist named Alan Guth is working late, scratching through equations that most of his colleagues consider an interesting curiosity rather than a serious line of research. Guth is trying to solve the monopole problem. He is not initially trying to solve the horizon problem or the flatness problem. He is just trying to figure out why we cannot find magnetic monopoles. And he finds something. In the notes from his notebook from December 7th, 1979, a date he circled emphatically with the words "spectacular realization" written in the margin. Guth describes a mechanism that not only solves the monopole problem, but solves the horizon problem and the flatness problem simultaneously. The mechanism is called inflation. Guth proposed that in the very first moments after the Big Bang, not seconds after, not milliseconds after, but in a window of time so small that describing it requires notation, like 10 to the power of negative 32 seconds, the universe underwent a period of exponential expansion. Not the steady, gradual expansion we observe today. Not even a rapid expansion, an explosive, staggering, almost incomprehensible acceleration of the expansion of space itself. In a time interval shorter than a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor of at least 10 to the power of 26. Some models suggest far more. A region of space smaller than a proton was stretched to a size larger than the observable universe today. Imagine taking a crumpled piece of paper and stretching it across a surface the size of a continent. Every wrinkle, every fold, every surface irregularity, smoothed out, flattened, erased by the sheer violence of the stretching. That is what inflation did to the early universe. And here is why it solves the three problems. The horizon problem dissolves because the regions of the early universe that appear causally disconnected today were actually in contact before inflation. They were close together, close enough to thermalize, to exchange energy, to reach the same temperature. Inflation then stretched them apart so violently that the signals from their contact can no longer reach us. But the contact happened. The uniformity was established before inflation tore the regions apart. The flatness problem dissolves because inflation stretched the universe so dramatically that any initial curvature was smoothed away. It does not matter how curved the pre-inflationary universe was. Inflation stretched it flat, just as the surface of a large balloon appears flat to an ant sitting on it, even though the balloon is a sphere. Stretch any curved surface by a factor of 10 to the 26th power, and it becomes indistinguishable from flat. The universe is flat today because it was violently flattened by inflation. The monopole problem dissolves because inflation diluted the density of monopoles to essentially zero. Even if grand unified theory had produced enormous numbers of monopoles before inflation, the subsequent expansion of space by a factor of 10 to the 26th would spread them so thin across such an enormous volume that the expected density within our observable universe would be less than 1. Perhaps far less than 1. The monopoles exist somewhere in the vast inflated cosmos. There are simply none close enough to us to detect. 3 problems, 1 mechanism, all 3 solutions falling out of the same calculation. Alan Guth published his inflation paper in 1980. The response from the physics community was, to use a carefully chosen word, electric. But inflation raised a question that was, in some ways, more troubling than the problems it solved. What was doing the inflating? The exponential expansion of space requires energy, not a little energy. An extraordinary amount of energy stored not in matter or light, but in the structure of empty space itself. Guth proposed that this energy came from a field, a quantum field permeating all of space, called the inflaton field. In the very early universe, this field was in a particular energetic state, a state of high energy that drove the exponential expansion of space. When the field eventually transitioned to a lower energy state, when inflation ended, the energy stored in the inflaton field was converted into the matter and light of the universe we know. The actual Big Bang, the hot, dense fireball of matter and radiation that Gamow and Lemaitre described, was not the beginning of the universe. It was the end of inflation. It was the moment when the inflaton field released its energy into the cosmos, filling the newly expanded space with matter and light. Before the bang was the inflation. Before the bang was the violent, silent, exponential expansion of empty space, driven by a quantum field whose energy we are still struggling to fully characterize. And that realization, that the Big Bang was not the beginning but a transition, an ending of one phase and a beginning of another, pushed the question of origins even further back. Because now the question was not just what was before the Big Bang. The question became what was before inflation. And this is where the science becomes genuinely strange. This is where the comfortable language of cause and effect, of before and after, of beginning and ending, starts to creak and splinter under the weight of what the mathematics is trying to tell us. Alan Guth's original inflation model had a problem. The inflation never cleanly stopped. In Guth's original formulation, the transition from the inflating state to the normal expanding state was like a phase transition, like water freezing into ice. And, like a phase transition, it left behind a landscape that was not smooth and uniform, but fragmented. Bubbles of the new phase, normal, post-inflationary space, formed and grew within the still inflating background. But these bubbles could never merge smoothly because the space between them was expanding too fast for them to catch up. Guth's original model produced a universe that looked nothing like ours. The transition from inflation to the hot Big Bang did not work correctly. This problem was solved independently by Andrei Linde in the Soviet Union and by Andreas Albrecht and Paul Steinhardt in the United States, who in 1982 developed what became known as new inflation and chaotic inflation. Refined models in which the transition from inflation to the hot phase happened slowly and smoothly, like water gently cooling below its freezing point rather than freezing suddenly. But in solving the graceful exit problem, the new models revealed something unexpected, something profound, something that, depending on your perspective, is either the most exciting idea in modern cosmology or the most disturbing. In most versions of inflation, once inflation starts, it does not stop everywhere at once. The quantum nature of the inflating field means that different regions of space will transition out of the inflating state at different times. In some regions, inflation ends and a hot Big Bang occurs, producing a universe like ours. But in other regions, in the vast majority of the inflating space, inflation continues. And in those regions where inflation continues, new bubbles of post-inflationary space form. New universes, each with their own Big Bang, their own period of radiation and matter, their own laws, their own physical constants. And around those new universes, inflation continues still, producing more bubbles, more universes, without end. This scenario, developed most fully by Andrei Linde in his theory of eternal chaotic inflation, describes a cosmos that is, in its deepest structure, not a universe at all. It is a multiverse, an infinite, eternally inflating background of space, constantly generating new pocket universes like our own. Each bubble universe is causally disconnected from all the others. No signal, no particle, no light can ever pass from one to another, because the inflating space between them expands faster than any signal can traverse it. Our Big Bang, our entire observable universe, our 13.8 billion year history, every star and galaxy and planet and living thing, is one bubble. One tiny, finite island of post-inflationary space in an ocean of eternal, accelerating expansion. And that ocean has no shore, it has no center, it has no edge. It has always been there, or it has been there for so long that always is not a meaningful distinction. Now we arrive at the heart of the question that has threaded through everything we have discussed, the question that sits at the bottom of inflation, at the bottom of the Big Bang, at the bottom of space-time itself. What came before? And here the most honest answer physics can give is this: we do not fully know, but we have suspects, and they are extraordinary. The first possibility is the one you have already encountered. Before the Big Bang, there was inflation. Before the universe we know was the inflating space-time of the eternal multiverse. In this picture, the universe had no beginning in any conventional sense. The multiverse has always existed, or more precisely, the question of whether it had a beginning is not well posed, because the concepts of time and causality may not apply to the eternal inflation background in the same way they apply to the universe we inhabit. This answer is uncomfortable. It does not give us an origin. It pushes the question back to, where did the eternal inflation come from? The second possibility is one of the strangest ideas in the history of physics. It was proposed by Stephen Hawking and James Hartle in 1983 and is called the no-boundary proposal. Hartle and Hawking asked a deceptively simple question. What if the universe has no boundary in time? What if, instead of having a beginning, a sharp edge where time started, the universe has a geometry in which time smoothly transitions into a spatial dimension near what we would think of as the beginning? To understand this, consider the surface of the Earth. The Earth has a south pole. It is a real location on the surface of the planet. But it is not a boundary. It is not an edge. You can stand at the South Pole and look in any direction, and in every direction you are looking north. There is no wall, no edge, no before the South Pole. The South Pole is simply a point where the coordinate system we use to navigate the globe, latitude, reaches its minimum value. Hartley and Hawking proposed that the beginning of the universe is like the South Pole of a four-dimensional space-time. As you approach the Big Bang going backward in time, time gradually becomes more and more like a spatial dimension. The sharp beginning, the singularity, the moment of infinite density and zero size, dissolves. In its place is a smooth, rounded, boundary-free surface of space-time. In this picture, the question, what was before the Big Bang, is precisely analogous to the question, what is south of the South Pole? Not unanswerable, not mysterious, simply wrongly posed. The universe has no boundary, no edge, no before. It simply is what it is, complete and self-contained. It is an elegant answer. Many physicists find it beautiful, but it raises its own profound question. What determines the geometry of that initial surface? What selects the starting conditions of the universe if there is no boundary and no external cause? Hartley and Hawking's answer, formulated in the language of quantum mechanics and known as the wave function of the universe, is that the initial conditions of the universe are determined by quantum probability, not by any external cause or initial state, but by the quantum mechanical rules that govern all physical systems. The universe did not need a beginning in their framework. It did not need a cause. Its existence and its properties are determined by quantum law, and quantum law is not a thing that was turned on at some moment. It is part of the fabric of reality itself. But there is a third possibility, one that is darker and more disquieting than either of the others. What if the Big Bang was not the first event in our universe's history? What if, before the Bang, there was a previous universe? The idea of a cyclic cosmology, a universe that expands, contracts, and begins again, over and over in an endless series of cosmic cycles, is ancient. It appears in Hindu cosmology, in certain strands of Greek philosophy, in the writings of Nietzsche. but it has also been given rigorous mathematical form by serious physicists. In 2001, Paul Steinhardt and Neil Turok proposed a model called the ekpyrotic universe, from the Greek word ekpyrosis, meaning out of the fire. In this model, our universe exists on a three-dimensional membrane, a brain, floating in a higher dimensional space. Adjacent to our brain is another brain, invisible to us, separated from us not in any direction we can point to, but in an extra dimension of space. These two brains attract one another. Over 1 trillion years, they slowly move toward each other. When they collide, the kinetic energy of the collision is converted into matter and radiation, producing an event that looks, from the inside, exactly like a Big Bang. The universe is born. It expands. Stars form, galaxies form. Life emerges. Civilizations rise and fall. And slowly, over the next 1 trillion years, the two brains once again draw toward each other, and the cycle begins again. In the ekpyrotic model, the Big Bang was not a beginning. It was a collision. It was the latest in an infinite series of collisions stretching backward and forward through time. The universe is not 13.8 billion years old. It is incomprehensibly old. The 13.8 billion years is merely the time since the last collision, the last reset. Before our Big Bang was another universe. Before that universe was another. Before that, another. In a sequence that may have no beginning and no end, stretching backward into a past that our universe cannot directly observe because the evidence was erased at the moment of the collision. There is one more possibility, one that begins not with cosmology or string theory or membrane physics, but with the strangest and most counterintuitive branch of physics ever conceived: quantum mechanics. In classical physics, nothing comes from nothing. Every effect has a cause. Every particle has an origin. Every event was preceded by another event. Quantum mechanics does not agree. In the quantum world, particles appear from nothing constantly. The vacuum, empty space, is not actually empty. It is a seething, violent, flickering sea of activity in which particle-antiparticle pairs constantly pop into existence from pure quantum uncertainty, persist for a tiny fraction of a second, and then annihilate one another. This is not speculation. It is a measured, experimentally confirmed reality. The Casimir effect, a force between two metal plates held very close together in a vacuum, exists because of the quantum activity of the vacuum, and it has been measured in laboratories. The vacuum is not nothing. The vacuum is something. A quantum field in its lowest energy state, but a state that is alive with quantum fluctuations. In 1973, the IUD physicist Edward Tryon published a paper in the journal Nature with the title, "Is the Universe a Vacuum Fluctuation?" He proposed exactly what the title suggests. The universe, all of it, everything that exists, all the matter and energy and space-time we inhabit, could be the result of a quantum fluctuation, a spontaneous event in a pre-existing quantum vacuum in which energy was borrowed from the vacuum and used to create a universe. The total energy of the universe, when you add up the positive energy of matter and radiation and subtract the negative energy of gravity, appears to be very close to zero. This is not a coincidence in Tryon's framework. A universe with zero total energy could arise from the quantum vacuum without violating the conservation of energy. It costs nothing to create. The universe is, in the deepest possible sense, free. But this answer, like all the others, raises its own question. If the universe is a quantum fluctuation in a pre-existing quantum vacuum, then what is that vacuum? Where did the quantum vacuum come from? What were its properties and what determined them? We do not know. And here is what is remarkable, what is staggering in the truest sense of that word. Each of these answers, eternal inflation, the no-boundary proposal, cyclic cosmology, quantum vacuum fluctuation, is internally consistent. Each is supported by some version of the mathematics. Each makes predictions or at least suggestions about observational signatures we might one day detect. And each of them, in the final analysis, pushes the question of origins back by one more step without ever quite resolving it. This is not a failure of science, it is the nature of the question. Because what came before the beginning is a question that seems to assume something. It assumes that there is a frame of reference outside the universe from which the universe's beginning can be observed and explained. It assumes that causality, the chain of cause and effect, extends backward beyond the moment of creation. It assumes that time is a road that stretches backward forever, even past the point where the road was built. None of these assumptions may be valid. The singularity, the infinitely dense, infinitely hot, infinitely small point that sits at the back of the classical Big Bang theory, is almost certainly not a real physical object. It is a mathematical artifact, a place where our equations break down because we are trying to apply general relativity in a regime where it does not apply. A regime where quantum mechanics becomes essential, where space itself is so small, so hot, so dense, that the smooth, continuous space-time of Einstein gives way to something we do not yet have the mathematical tools to fully describe. The physics community has a name for this regime. It is called the Planck scale. It corresponds to times shorter than 10 to the power of negative 43 seconds after the Big Bang, to temperatures higher than 10 to the power of 32 degrees Kelvin, to distances smaller than 10 to the power of negative 35 meters. At the Planck scale, space and time as we know them cease to be meaningful. They become quantum mechanical. They fluctuate. They do not have definite values. The smooth, continuous fabric of space-time that Einstein described breaks down into something grainy, foamy, probabilistic, something we have not yet been able to characterize with a complete and verified theory. This missing theory, the theory that combines general relativity with quantum mechanics, is the most sought-after achievement in theoretical physics. It goes by several names. Quantum gravity, the theory of everything. Some believe the answer lies in string theory, others in loop quantum gravity, others in approaches with names that are known only to specialists. None of these theories has yet been confirmed by experiment. But even without a complete theory of quantum gravity, we can say something meaningful about the question of origins. We can say something that is both scientifically honest and philosophically profound. We can say that the concept of before may not apply to the beginning of the universe, not because the question is unanswerable, but because time itself may be part of the universe, part of the thing that was created, and therefore cannot extend beyond the boundaries of what was created. Think of it this way. You are inside a room. The room has 4 walls, a floor, and a ceiling. You can move in any direction within the room, but you cannot move to a location that is outside the room while remaining inside it. The room is the totality of the space available to you. Time may be to the universe what the room is to you. Not an infinite corridor stretching in both directions, with the universe sitting somewhere in the middle of it, but a dimension that is part of the universe, created with the universe, and bounded by the universe's beginning. If time began with the universe, then before the universe is not a moment in time. It is not a location on the timeline. It is simply not a category that applies. And yet, this is not the same as saying the universe had no cause. It is not the same as saying nothing existed before. It is simply saying that whatever existed before, if before is even the right word, existed in a mode of being that was not governed by the time we know. That whatever came before was not earlier in any conventional sense. It was prior in some other sense, a metaphysical priority rather than a temporal one. This is where physics, even at its most rigorous, touches the edge of something that feels like philosophy, where the equations point toward questions that the equations cannot answer. What do we actually know, and what do we merely suspect? We know that the universe had a beginning approximately 13.8 billion years ago. This is established beyond any serious scientific doubt by the expansion of space, the cosmic microwave background, and the elemental abundances of the early universe. We know, or very strongly suspect, that the standard Big Bang, the hot, dense beginning, was preceded by a period of inflation. The evidence for inflation is strong: the flatness of the universe, the uniformity of the CMB, and the pattern of small fluctuations in the CMB that map precisely onto the quantum fluctuations predicted by inflationary models. We suspect, but cannot yet confirm, that inflation was eternal, that our universe is one of many pocket universes in a vast, inflating cosmos. The multiverse is a natural consequence of the best inflation models. But because other pocket universes are causally disconnected from us, we cannot directly observe them. The multiverse is, at present, an inference rather than an observation. We do not know what happened before inflation, or whether the question of before inflation is coherent. We do not know what determined the initial conditions of the inflationary field, or why there was something rather than nothing. We do not have a complete theory of quantum gravity, and without it, we cannot fully describe the Planck scale regime, the moments closest to the beginning, where the universe's birth actually occurred. These are not temporary gaps waiting to be filled in by the next generation of telescopes. They are deep, structural questions at the boundary of what physics can currently ask. They require new mathematics, new concepts, possibly new ways of thinking about time and causality that do not yet exist. There is a coming generation of instruments that may push the boundary of what we can know. In 2034, if current plans hold, the European Space Agency will launch a mission called LISA, the Laser Interferometer Space Antenna. It is a gravitational wave detector, not one detector on the ground, but 3 spacecraft flying in a triangular formation, separated by 2 and a 500,000 kilometers. The most precise measurement instrument ever constructed by the human species. Gravitational waves from the very early universe, from the moments of inflation, from the dynamics of the inflaton field, would carry a specific signature in the gravitational wave background. If we can detect this signature, we will have direct observational evidence of the inflationary process. We will have, in a sense, heard the sound of creation. We may also learn, from the precise pattern of these gravitational waves, something about the energy scale of inflation, about the specific nature of the inflaton field, about the quantum mechanical processes that drove the exponential expansion. We may even see, in the most optimistic scenarios, evidence of the collision of our bubble universe with an adjacent bubble universe in the multiverse. A bruise on the CMB, a distinctive circular pattern in the distribution of temperature fluctuations. That would be the scar left by a cosmic collision billions of years in our past. If that signature is found, we will have confirmed not just inflation, but eternal inflation. Not just the Big Bang, but the multiverse. The universe will have told us in its own language of ancient light and gravitational waves that it is not unique, that it is one of many, that the cosmos is not a house but a neighborhood, and the neighborhood extends further than we can see. And so we arrive, at last, at the edge, the place where the questions become philosophical rather than scientific, because the science has not yet caught up with the depth of the inquiry. What existed before the Big Bang? The most honest answer is, we do not know, but the shape of our ignorance is meaningful. We know that the question of before may not be applicable in a simple temporal sense. We know that the universe we inhabit may be one of many, generated by an eternal inflationary process that had no beginning in time because time itself was generated in the process. We know that quantum mechanics allows for the spontaneous creation of something from nothing, that the vacuum is not empty, that reality is restless at its deepest level, that the boundary between existence and non-existence is not a hard line but a quantum probability. And we know that the singularity, the idea that the universe began from a mathematical point of infinite density, is almost certainly not a real physical description of the beginning, but a placeholder, a gap in our understanding marked by an equation that broke down at the moment it was most needed. What sits in that gap, what the true nature of the beginning actually is, remains unknown. But here is what is perhaps most remarkable of all. We can ask the question, 13.8 billion years after the beginning, whatever that beginning was, matter organized itself into atoms. Atoms organized themselves into stars. Stars forged heavier elements and scattered them across space. Those elements organized themselves into planets. On at least one of those planets, some of those atoms organized themselves into living creatures. Some of those living creatures organized themselves into beings capable of language and mathematics and abstract thought. And those beings, you, can lie here in the quiet dark and ask, what was here before any of this? The universe created from its own substance a form of matter that could look back and wonder about its own origin. Whether that is a coincidence or a necessity or something with a name we have not yet invented, that question too remains open. The cosmos is not finished with its mysteries. Neither are you. Whatever came before the Big Bang, it created a universe vast enough to be humbling, old enough to be incomprehensible, and strange enough to remain, even after centuries of inquiry, almost entirely beyond our grasp. And yet, here we are, reaching. Sleep well.